Thailand, Chulalongkorn University, from Ho Chi Minh City, Dr. Hui, Tamba from Libya, yeah, and Mr. Anur from oil company also we invite from oil company to share his knowledge regarding EOR, chemical EOR. So in this morning, you will be share regarding steam assisted gravity knowledge. So my student, this is valuable time for you. Yeah. Now we learn from professor from overseas. He will explain in English. So please don't be shy. Follow, listening, because I hope Professor Shin, you can send to Rifal Fauzi one of question and the answer. We will give the question in the final exam in this semester.
Okay.
So students should be follow carefully because one of question from this topic in this morning from Professor Shin. Yeah. And if you have question, don't be shy. If you cannot speak in bahasa English, it's okay. Just say in bahasa Indonesia. In here we have your senior, yeah, Rifal Fauzi and Bob Duafa, yeah, Bob Duana, yeah, Bob Duana, your senior, 2013, Bob, 14,
13 actually, yes.
13 ya,
Yeah.
2013. Bang Bob ini 2013. Now he take combined program, master degree and PhD degree combined program under supervision Professor Shin. Yeah, if you cannot speak in English, Bang Bob and Bang Rifal can help you. Just ask in bahasa Indonesia, no problem. I hope you very active in this time. Yeah, Professor Shin has many experience from the oil industry, and after that he joined in university, in Inha University, and up to now he's still active in oil industry as consultant or get some project from government and oil industry. So he expert in EOR, especially and steam flood. So this is very valuable time for you. Please use this time, yeah, ask something other topic regarding your introduction of your. Oke, Rival, please absennya jangan lupa Rival.
Yes,
And
doctor.
recording this class, we will record this class, Professor Sin, and we hope you allow us to record this class in this morning. Are you agree, Prof? We record this class?
Me?
We'll record.
Yeah, no problem.
Okay.
Yeah, there's no secret.
Okay. Okay. Before you deliver your class, please, maybe you can give some speech to our student. Please,
Okay.
Prof.
Okay, good morning, everyone. Thanks for invitation for lecture today. So your introduction to EOR course, Kuliah University. So today I try to introduce one of the heavy oil recovery process, especially for oil sand recovery process is called SAGD. So you can already know that some terms is a steam and gravity. Right? There's a two mechanisms exist in this special steam flooding process. So actually it's quite big topics as an introduction, so I just spend a lot of time to eliminate some of the slides which what I had before. And probably I have the two sections. One is the introduction for heavy oil, and the other one for executive process. So your questions probably follow after finish my presentation. There is more. So let me know if something problems to hear my voice. It's okay?
Okay, Prof.
Okay. Okay, so as I mentioned, some heavy oil and in-situ recovery methods in centipoid. But if the viscosity high, means in primary recovery factors is very low. And we need something to do, reduce the viscosity. That's why you use the thermal. That means inject heat. One is the popular steam. It's a thermal process. It's a steam injection process. And we're not talking about the oil shale because oil shale is oily shale. Exists as a kerosene. So this is not oil yet. So that means you have to cooking. You have to heating above 340 degrees C to convert the kerosene to oil. So United States have this whole bunch of the oil shale. But I think they doesn't have any chance to develop this one because they have shale oil and maybe some energy transition, and the demand for oil and gas may be decline or constant, right? So it's a situation change. So heavy oil and oil sand is two countries. One is the Venezuela heavy oil. It's a 2 trillion barrels. And Canadian oil sand is also very close to 2 trillion. So total world revenue at this time, maybe end of the last year, probably close to 1.7 trillion barrels of world total reserve. But these numbers actually resources. So only 10 or 20% of resources already converted to reserve in these two countries. And we are talking about for unconventional resources. So that means it's difficult to produce. Why is it difficult? We have two issues. So you already know from the Darcy equation, right? And for flow rate, it's a function of permeability and viscosity and delta P between reservoir pressure and wellhead pressure. And we're talking about these two issues, permeability. How easily your rocks allow to move the fluid to one place to another place. The resources for shale gas and tight gas cases, so you already know the gas doesn't have any issues in viscosity. But why is it difficult to produce? Because shale and tight sandstone, they have very low permeability. So if you increase production of the oil, you have to reduce viscosity and increase permeability. So if your reservoir low permeability or high viscosity, you have problems to production. That means low recovery. So shale gas and tight gas have problems in permeability, and how you can increase your production by increasing permeability. How? Hydrofracturing. You inject high water, high pressure injection, and you just create some fracture. That means to break your rocks and then produce through the fracture areas. And now for oil sand cases, we have the problems in viscosity. In heavy oil and oil sand, how you can increase production. Maybe you have to reduce viscosity before main production. So that's why thermal process actually apply to reduce the viscosity. And these two issues, so that's why unconventional resources all the time have the issues in one or two, right? But basically either lower permeability or high viscosity. And you have to solve these issues to produce. And even for same oil, but sometimes they have different recovery process. This one actually viscosity change by log scale, and this x-axis is the temperature. So that means this oil heating up, that means your reservoir temperature increase by depth, right? So dipping reservoir, even 10 degrees C, the viscosity of the oil, 1 million centipoid is a huge number in viscosity. And this one actually heating your reservoir around 55 degrees C. That viscosity of the oil reduction maybe 1,000 or 2,000. That means enough to mobile. So that's why Canadian Athabasca oil sand areas, their temperature is very low because it's shallow and Canada is very cold. So average reservoir temperature all around close to 10 degrees C. And Orinoco Belt in Venezuela, they have probably 500 to 800 meters depth. They have high geothermal, and then the temperature of your reservoir in Orinoco Belt close to 50 to 60 degrees C. And same oil, they probably reduce the viscosity decrease down to 1,000 centipoise. That's why in Orinoco, they don't need to produce the thermal. They can use the cold production. So cold production, just opposite definition. That means they don't use any thermal, no steam. But if you apply cold production, you can produce, but recovery factors less than 10%. Maybe maximum 15% depend on viscosity. Even the viscosity is different in same reservoir. But if you want more high recovery factors in Orinoco Belt, you have to apply thermal process. And then maybe recovery factor from 10 to 50%. Because in Athabasca for SAGD process, recovery factor up to 50 to 60%. And that's why it's very important for steam process, what kind of effect they have on viscosity. The right hand side, you have the viscosity. So you already saw the graph. Low temperature, high viscosity. So ABCL is a PR is a different location in Canada oil sand basin. AB is Athabasca oil sand. CL is Cold Lake, and PR is a Peace River. That is a short naming of regions. And Athabasca, the highest viscosity, more than million centipoise. And lowest one is the Cold Lake areas. They have 30,000 centipoise. It's low. It's a big change in there. But if you once inject steam and heating up, this one actually converts to around 10 centipoise range. But be careful for steam. You make steam at room temperature around, or pressure, atmosphere pressure is standard condition. You make 100 degrees C. You heating up to 100, you can make steam. But your reservoir actually is not atmosphere pressure. It's depends on the depth. But in oil sand cases, the deposition depth around 100 to 300 meters is very shallow. Usually heavy oil deposition actually very shallow compared to conventional oil. If you can make an assumption for 1.0 megapascal to 4 megapascal ranges of your reservoir pressure, that means you make steam with high temperature. So that's why you have the vapor pressure for water. So that means 100 degrees C, you have the 100 kPa. But your reservoir 2000 kPa, you make more than 12 degrees C. Below that temperature, you have the liquid. All right? So that's why this one is a vapor rise slope. So below this line, same temperature, but if the pressure high, you have the liquid in this portion. Maybe this portion is a liquid, and this one vapor. So it's very difficult to imagine. So one case is when I visit Kazakhstan, one company, they doing some steam process, but the effect of the production, so recovery is very low. So I asked them, what is your reservoir pressure? and what is your steam pressure. And they actually inject, they make steam at the surface, but in downward, they inject this condition. That means they inject hot water instead of vapor. Right? So that kind of things is to be careful, but steam is very effective to reduce the viscosity. And oil sand is a sand plus bitumen, so it's unconsolidated. So this one is not rock, not consolidated rock. So that's why unconsolidated, they mixed with the bitumen with high viscous. So two important information for bitumen, the heavy and high viscous. So that means the oil quality is not good. That means it's cheap compared to conventional, because why the oil price change? Which one is the expensive oil? Which one is the cheap oil? Because you use most of the oil to distillate to gasoline component. So heavy oil, they have more aspartames. Instead light the alkane or light for condensate compositions or naphtha. So less components. So that's why this one is cheap. Why they, so from the beginning they was viscous or they was heavy? No. In when they generate hydrocarbon in underground, they was a light oil. But I mentioned the deposition of oil sand and heavy oil is shallow. How they move? So they make in source rock with the shale formations. In organic rich shale, they generate lots of hydrocarbons. And hydrocarbon is lighter than water. And they moving from bottom to top or deep location to shallow location by buoyancy, right? So that's why they move up to, they meet some trap structures. During that migration of the hydrocarbon, actually they experience biodegradation. So that means the grade actually make worse, that means degrade by bacteria. That means the biological activities help them to degrade. So that's why we call it a biodegradation process. So where the bacteria stay, they live in water formation. So that's why the light oil, they move to some place to shallow, and during the migration they contact water formation. And then light component from the light oil disappeared, and the remaining oil getting heavier and getting viscous. That's why they make the tar sand and extra heavy oil in shallow locations. And oil sand is the good thing, it's easy to extract by using hot water because it's a water wet. So water wet is very important concept in petroleum engineering. Water wet means your sand grain covered by water, and that means the oil actually between this four space. So that means you can easily extract from this sand grain. The same oil sand in United States, in Utah, they have the oil wet. So oil wet means the oil is sticky around surface of the sand grain. So that means recovery is more difficult. So that's why in Canadian oil sand is easy to extract by using water, especially hot water in a mining process. So API less than 10 sometimes and viscosity high. So if you, for example, for viscosity, honey is close to 3,000 centipoids. You can just imagine how viscous the bitumen. Sometimes 5 million centipoids. That is a solid. No mobility. That's why if you want to really produce oil sand, you have to reduce viscosity. Right? So that's why you need inject steam. And in Canada, this one is a Canadian regions, and there are first province is British Columbia, And second one is the Alberta. So most of the oil, or more than 70% Canadian oil, located in Alberta province. So this the boundary in this area is the Rocky Mountain. So there are two big cities. One is the Calgary. Most of the oil company head office located in Calgary. And one is the capital city actually is Edmonton. The University of Alberta located in Edmonton and University of Calgary located in Calgary. So in these three regions is Athabasca area and Cold Lake area and Peace River area. So previous slide I mentioned three different locations, the oil viscosity. So this one actually more than 70 or 80% oil located in this Athabasca area. So that's why they have lots of project in and upgrading facilities in this location. And oil sand, how you can produce oil sand, there are two things. Mining process, because it's a shallow at the surface mining, they do, and they separation with big vessels, and they make bitumen. And then bitumen is a low quality of hydrocarbon. That means hydrocarbon is component hydrogen and carbon. So these days hydrogen is very popular, right? You can separate from the hydrocarbon. So that's why these days 95% of hydrogen production from fossil fuels, because hydrocarbon compositions, they separate. They adding steam, because steam has H2O, they also have the hydrogen. So they separate from that one. So they upgrade means they make light oil, convert to light oil, and they make synthetic crude oil, we call SCO, synthetic crude oil. And then they send to refinery. And the other things for oil sand produce SAGD like this, and steam injection, because there is not open pit, that's why we call in situ. So in situ recovery method, you can inject steam, produce and separate, and then make bitumen. And usually you can send this one to upgrading, but upgrading facilities integrate usually for mining. Why? Because the SAGD process for each project, the standard production rate close to 30,000 barrels. But the upgrading facilities more than 150,000 barrels. It's a huge. So that's why they can 24 hours they can provide and feeding to these upgrading facilities around plant in mining site. And how viscous oil you can transport by transportation using pipeline. You're just mixing with light oil. So the light oil component we call diluent. So that's why bitumen plus diluent, so they call dilbit. How they make it? Maybe 30% of condensate mixed with 70% of bitumen, and they make 1 barrel. So that's why they make around 300 centipoise by diluent mixing. They transport this one to United States. More than 70% of the bitumen they actually send to United States, because the United States have heavy oil refineries. That's why they buy very cheap bitumen and they distillation in the refinery. They extract lots of light oil or gasolines and they make money. In Canada, they actually only few number of distillation or refinery. Couple of things is they actually shortage of the refinery. That's why they have to send to United States. And just quick for review for mining, they actually shovels 100-ton size, and these trucks 400 tons trucks. So you have the 4 shovels into this truck, and they generate 200 barrels. So they send this one to big vessels, it's a separation vessels with hot water. So water temperature maybe 60 to 70 degrees C, and they put oil sand and they stirring centrifuges and the heavy sand particles drop, and light bitumen actually frozen, the flotations, and they remove this one and sent to upgrading facilities. Because bitumen has very reduced number in hydrogen, so that means heavier part in hydrocarbon, light oil have more hydrogen component compared to heavier. And heavy oil, they have more concentration in carbon because carbon is heavier than hydrogen. So people in upgrading facilities to change how you can change the quality from bitumen to light oil. There are two methods. One is just remove or reduce number of carbon, and then you have a relative high concentration of hydrogen. That means light oil. That's why how you can make or remove the carbon with coking. The coking actually is a carbon, and hydrogen addition, that means you actually high temperature and cracking the hydrocarbon bondings, and you add hydrogen and light oil. So coking process is an old process, and you inject 100 barrels of bitumen, you can only 85 barrels because 15% convert to coking, you remove. And hydrocracking is a new technology compared to coking process. But good thing is no coking, no headache, right? But they add hydrogen, they actually 100 barrels bitumen get into the facilities, you can produce 103 barrels because you add hydrogen to make light oil. So that is the upgrading facilities. And these days for hydrogen society, how you can make, even they don't use this one for gasoline anymore in the future, maybe 2050 or 2060, you can convert this one to hydrogen production facilities by coking, or you can add more, you can generate more hydrogen. So just separation process. And steam process, one of it is the cyclic steam stimulation. You inject steam and wait until steam vapor phase convert to liquid phase. And they heating up and they produce back. So this one actually one single well process. So one well, inject, waiting, and produce. So single well operation, but the process actually inject soak production, no more production, you inject again, so you make a cycle. So one key parameters to evaluate the efficiency of steam process actually is steam oil ratio, SO1. These numbers should be low because the definition is 1 barrel of oil you want to produce, how much barrels of steam you have to inject. So that means if the numbers is low, maybe you have to a better process, less steam required. Less steam required means you don't need much energy to boiling the steam. So the reservoir quality actually less bad quality compared to other areas in Cold Lake and Peace River. They're using for vertical side CSS or sometimes horizontal wells. You can do horizontal wells also. So this one actually steam oil ratio 3 to 6. So that means 1 barrel of bitumen you want to produce from this process, you need 3 barrels of steam injection or up to 6. These numbers should be lower, it's a better performance. And final recovery, maximum 25% using this process. And second process, you use 2 horizontal wells. So since 1990, this one is commercialized, start to commercialize. And first commercialized process in Mackay River project, so which I will explain later in SEGD sections. They start almost 2000. So now it's almost a 20 years history for commercialized in SEGD. And these are actually two parallel wells drilled, and upper well only injects steam, and steam getting up, and they condense to liquid and reduce viscous oil down to your production well. So injection well and this one production well. The distance, this one 5 meters apart. These are actually continuous process. Because the previous one, this one is a cycle, inject, soaking, production. So the time is different, right? Injection time, but exactly continuous injects, continuous production. So this one actually up to 70% in pilot project for final recovery factors. And steam oil ratio less than CSS is a 2 to 4. So less than 4, we can make money from this project. And the steam process, lots of people criticize why you use the steam. Because you using the water and you burn the boiler using natural gas. And people think about, okay, how we can reduce viscosity except heat. And they say, because from the drill bit, you may already know, right? You mixing with light oil, you can reduce viscosity. And they apply this technology and they inject for solvent into the downer with saggy foam, same horizontal wells, but instead inject steam, they inject solvent. But this process is actually very slow because it's a diffusion in the molecular levels and low production. So probably less than just probably 5 cubic, so that means around 30 barrels per day from the pilot. So they did in pilot project this one, but only interface they have chance to reduce viscosity. The problem is how you can expand or quickly replace the interface volumes. That is very difficult, and also you cannot control. And inject solvent actually somewhere near reservoir, but we don't know where they're going. So we call this as a solvent loss. The loss of solvent into your reservoir, that means no return to the surface more than 50 or 60%. So that's why they lose. But the idea is very good because they do no steam injection. So that means no greenhouse gas emission. And also this mixing, they upgrading. Maybe some heavy component precipitations happen, that means the remaining oil is lighter. There is some positive things, but real problem is production rate is quite low. And they shut down this project after 7 years pilot. So we call this as a Baypex process. So now we touch two things, right? For steam process is good, they lots of production, but you use lots of water and energy. And Baypex production is rate low, but its idea is good because no steam. Now people think, how about we can mix? So hybrid, steam and solvent co-injection. And you can, the synergy, some of the heating to viscosity reduction and the other from solvent for dilution, they reduce the viscosity. And they can keep oil production is a higher level, and also at the same time you can lower the steam oil ratio. So there are some things between these two, it's hybrid. But sometimes new guys, they say instead of the solvent, you can also solvent heating up, they phase change happen. So phase change happen means the vapor condensed to liquid, they release energy. But the energy they observe during the heating is different for individual materials. Maybe after class you can looking at what is the latent heat. LA, P, and P, latent heat. You looking at latent heat of water. So water probably more than 2000 kilojoule of the energy, 1 kilograms, but for solvent maybe 300 or 400. So that means the solvent doesn't have much energy needed to vaporize. But why the water they have, why we use water? Because you have to carry the energy from surface to downward. That's why same amount or same volumes of materials carry more energy from surface to downward. That's why it's very popular to use the steam process. Because water compared to solvent maybe 8 times higher latent heat they have. Maybe alcohol in beer, that alcohol, maybe they have around 800 kilojoule, the level. But still is the 1/3 of the water compared to water, right? So that's why water is easily you can get access. And they have high latent heat. That's why when the phase change happen, they can carry lots of energy to other place. That's why in Korea, cold time in the winter, they actually circulate the water, heating water, right? Hot water circulate, they release the energy to your room. It's the same thing. And then one of the typical things ES SAGD is expanding solvent SAGD process. They actually co-inject steam and solvent. But different type of solvent, they have different recoveries. And they think, okay, maximum cases is a hexane. Why hexane co-injection with steam? They bring more production. And then they think, okay, steam maybe at this pressure, 212 degrees C, they have the phase change happen. And they select hexane is very close to steam, water, to at this temperature convert the phase. So that's why you have to select which one have the very similar vaporized pressure and temperature with main steam process. That's why in steam with hexane is the best performance. So heavier one is better. Okay, so I've done for heavy oil introduction part and go to for SAGD. So SAGD, as I mentioned, we have the 2 horizontal wells drilling and then steam going up at the interface with the cold reservoir, they condense, and condense is heavier, right, and liquid, and they down to gravity to your production wells, and you can continuous production. And from the beginning, you have the rising and then expanding. So preheating means there are 2 wells 5 meters apart and no communication, no flow. So that's why you have to heating up this area to make mobility first by circulate steam in these 2 wells. And then later, you inject lots of steam, but no production, that you have to shut down, right? So that process we call wind down. Wind down means you won't maintain your reservoir pressure by non-condensable gas injection. Non-condensable gas injection means non-condensable gas is a typical non-condensable gas is nitrogen and methane. Methane gas you can just compress. You cannot make liquid. That's why you have to frozen. That means below minus 162 degrees C to make liquid, not ice, right? So that's why the non-condensable gas actually depend on the temperature change. They didn't change the condense. Why we concern about condense? If you condense from the gas to liquid, the volume actually 600 times reductions. So that means inside, okay, for example, 600 standard cubic feet of natural gas condensed to 1 standard cubic feet. That means inside your reservoir actually empty place happen. Condensed, this pore space actually empty. And then there are some flux, they change, so no production. So that kind of things you have to prevent. So later, injection steam doesn't make any economics. You have to, instead of steam, you have to inject non-condensable gas to maintain the pressure. This one actually typical CAGD process stage, preheating stage, and steam growth, then mature and wind down strategy. And this one usually for CAGD production around steam oil ratio, but C means cumulative. Cumulative steam oil ratio means total average up to now. So this one is around 2 is a very good performance. And production rate per day, average 100 cubic meters. So 100 cubic meters around 629 barrels. It's a typical things in SAGD. And then SAGD performance is very sensitive to geology and where you drill and what type of completions and how you can start up. You can start for preheating with inject or directly steam injection or circulation. And what kind of pump you use and operation strategy also impact SAGD performance. And this one for rock, oil sand phases. So black is oil sand and bitumen. White color is the shale. So phase 5 actually completely shale. So we have to determine which one have the blocking the flow, no production. So we can select, okay, F1, phase 1 is good, very clean, is a sandstone, no shale volume. F2, this one is a sandy IHS. So IHS means inclined heterolithic stratification. That means this shale area actually inclined, right? They have the dip. But what is the size of this one? Continuity. So we can consider from here maybe F1, F2, and this one also lots of volume of shale, but they broken. That means fluid can flow. The steam can pass through this one. So that's why in page 1 we can include phase 1 to 10 from these pictures. And 5 and this one, maybe steam cannot pass through to vertical direction, right? But problem is how extend these shale barriers. That is the key things in SAGD process. And for, you already know for logging, and this one is a gamma ray, so we have to detect which one is a clean sand. So left side, this one is a clean, but this one, maybe some of the V shale volumes they have. Maybe steam maybe pass or delay in this part. So that's why interbedded sand, interbedded shale barriers is very important. They are very critical, but how they continuity to horizontal directions. And this one is resistivity, right hand side is oil. So this one actually sand body. We define as a pattern. And this one for thickness. So these bubbles actually production rate. So big bubbles actually correlate with the dark colors. So dark color means the reservoir thickness high. So that's why SAGD process, thicker reservoir, better performance. At least in commercialized, 15 meters or 20 meters reservoir thickness should be guaranteed to produce high oil production from SAGD process. So that's why the geology is very important. For example, this one, maybe half of the part of your horizontal sections is located in very thin reservoir. That's why the bubble size is very small. Even the green part is oil, the other part is water. It's small. So that's why first things you have to check what is the net pay thickness. And this one for real maps is cross sections. So this one is a SAGD base. So this one you have to drill. But below this one you cannot produce because this one is a gravity. So above production wells you can recover by gravity, but this one you can't. So that's why you lose some of the reserve. So some people they think, okay, maybe we can drill in this one. Okay, because we want to capture this part. How about this part? They locate in the water formation, right? So no production. That means above this one, no production. You can only produce this one. So you have to make the balance. So that's why you have to avoid this kind of shale barriers or some water formation. So that's why these guys locate the horizontal wells above this one. Right? And how you can produce this one and drilling. So you first drill bottom hole, production well first, and second well injection wells to follow these well trajectories. That's why you need some magnetic guide tools. And this one during the MW they follow these trajectories, and you can make a parallel. So only the constant 5 meters vertical separation with magnetic guide tools. And circulations, how you can circulate? Maybe you can one tubing to inject steam. But once you release steam here, this distance around 800 meters. And during the traveling this location, they lose energy and they doesn't have the vapor. Maybe steam already changed to condensed to hot water. That means the heat release amount getting smaller. And they change, okay, we maybe separate two tubings. Inside big tubing, they have the small size of the tubing, inner tubing. And they release two positions. And one is the heel, one is the toe. And you can, these days, every 100 meters, they have some valves to control valves to release the steams in more homogeneous or equivalent. And production wells is very simple, right? And you can just one tubings and production. And we have lots of thermocouples to check the temperature around 800 meters, how you can control. Which one is cold, which one hot? Because cold means no production. So how you can managing that part of the cold production areas. And this one to sand control, because oil sand unconsolidated sand. That means you have a high risk to produce sand. So that's why your tubing or liners, you actually make hole, slot. We call this one as a slot. So this slot size is actually smaller than sand grain. So that's why you need sand grain particle distributions analysis for design this slot. So this one is a liner you can make, or sometimes you wire wrapping your caging or tubing. But this tubing have the holes inside, right? And fluid actually go into between the wire, like this, right? In here, the wire, between the wire, they have some space. And they get into this one. So good things for wire wrap screen, very strong, and they lots of exposed areas. That means they can produce or accept more fluid than slow liner. That is the type of the sand control unit. And this one is a pump. Some cases you don't have any pump here. It's a wellhead. But they have to inject some gas. And gas actually light, and they mix and lifting with the liquid. And you have the very popular load pump here. And the other one is a ESP pump, electric submersible pump in downer. So you have the electric wire and connect the motor in downer, and they suction, they produce. The other one is a very popular for unconsolidated heavy oil cases. It's a PCP pump. It's a progressive cavity pump. That means you have the load actually like this. At the surface, you rotate this guy. Rotate and pump, right? Electric motor. And this empty cavity actually move to this direction. And they deliver the fluid and even the sand to the surface. So most popular one is the ESP pump. In some cases, you have the PCP pump if you expect lots of sand production. And for monitoring, you need for 4D seismic because you can distinguish some areas produce or some areas non-production because you inject steam. The produced areas already occupied by steam. Steam is a vapor and hot temperature and seismic amplitude change. And you have, okay, this one, you have the steam chamber here. But cold area looks like make cold, doesn't have any steam. So that kind of things you can monitor how big our steam chamber and where along the horizontal wells which sections or which part we doesn't produce. And also you have some observation wells with drilling, couple of observation wells to check where the vertical sections steam temperatures increase. Okay, we have this one is a pageant. That means already steam occupy this location. But you have some from the horizontal wells, some middle point or close point, 4 point, you can drill. But if we want one more observation drilling, that means money. Because its operation costs several $100,000. And almost finished. So SEGD operation facilities, you need water. Right? And then you make steam generation, boilers. And in boiler, depending on the type of the boiler, you make 70% steam and 30% liquid, and you have to separate for steam because 100% steam you have to inject. And from the production side, you produce oil, gas, and water, and they separate. Okay, water, they return to cycle to water softening treatment, and they recycle. And gas, maybe from the beginning they can flaring, but these days they can't by the rule, the government regulations. And they, bitumen, maybe you can tracking if the small production, but sometimes you have to usually have the pipeline for sales. And water, some water you can actually dispose with the high content of the solutions they have. So this one is a cycle. So most key facilities, water treatment facilities, steam generation, boilers, and separation, and production treatment. Because in some production, even the once you separate, but some oil, they have some water or gas. And also water, they have some oil or some gas. So you have to more secondary or next stage separations to treatment for production fluid. And this one for field locations they have. And if you cite, okay, this one for boilers. And they sent the steam to the field to this direction and production this direction. And this one is facilities. So they have the de-oiling or de-watering and water cycle, water treatment. And sometimes because for diluent you need the diluent. And also diluent actually some cases for easily separation of your bitumen from the water. So that's why sometimes you have the diluent process. So that kind of things you can easily find at the field. So oil sand, they have lots of more treatment before production. You have the boilers and steam injection. That means it's big facilities. One means this facility to business. Maybe some EPC. Company, the construction company I own to this business because it's a big money because they construct some facilities, right? I think that what I have so far, and maybe we have some time to questions, maybe.
Okay, Professor, thank you very much for your presentation. And for students, please unmute your voice if you have question. You can ask in bahasa Indonesia. Boleh tanya pakai bahasa Indonesia. Nanti akan diterjemahkan.
So I have to answer in Indonesian.
No, no, no.
Speak in Korean if you want.
Baha, right?
No.
Okay, next time maybe I can learn from the Bob and
No, Professor.
Ayo, mahasiswa-mahasiswa sekalian, our student, please give question to Professor Shin. Don't be shy, okay? How about last time, Rifal Fauzi with Dr. Hui? Any student
Uh,
give question, right?
yes, doctor, like 3 or 4 students asking question.
Okay. This morning, I hope more student give question to Professor Shin. Halo, halo, halo. Morning.